Hello folks, welcome to CS412 Software Security. This is the speedrun of OX06 Mitigations. Today we will talk about different kind of attack paths and possible stopgaps on how we can stop exploitation of a bug in a program. The goals for today are to understand data execution prevention or DEP, ASLR, address-based layout randomization, stack canaries, safe exception handling, and fortify source as core mitigations that are deployed on all the different systems today. You'll have to be able to discuss trade-offs between cost and utility of a mitigation, and also know the limitations of mitigations, as in what can it protect against and what does it can it not. Mitigations are a very special kind of defense. They assume that programs have vulnerabilities because any kind of large application will have some kind of remaining vulnerabilities. So mitigations assume the existence of these vulnerabilities and try to make it harder to exploit a given bug, right? So instead of just allowing an attacker to exploit a bug, mitigation will stop the attacker from doing so and usually terminate the application as part of the process. The bug remains in the program, so the mitigation does not fix the bug and does not prohibit the denial of service per se. They simply limit a common attack vector. Mitigations may change the hardware, operating system, runtime, or software, and as we'll see in a bit, mitigations must be low overhead. Because if there would be no bug in the program, then paying for the mitigation in additional cycles or slowdown would simply result in unnecessary cost. Right? So mitigations are therefore very cheap to deploy. Now, this is the model for control flow hijack attacks that we discussed in the last class. And we could actually build defenses on all of these layers, from memory safety to integrity to confidentiality and flow integrity. If we don't stop an attack at any of these points, for example, code corruption attacks, control flow hijack attacks, or data only attacks, then the attack will actually succeed and bad things may happen, right? So all of these defenses or mitigations can be enforced at one of these boxes, one of these nodes in this graph. If we look at what kind of mitigations are actually deployed in practice, we see a somewhat weird or interesting picture as academics, researchers, practitioners proposed hundreds of mechanisms. Only a very small set of a few mitigations were actually adopted in practice. Now, we're asking ourselves what kind of factors increase the chances of adoption. And interestingly, the mitigation must solve a most imminent problem, right? So the mitigation must be able to protect against a certain exploitation style or other kind of problem that is currently imminent and broadly and widely abused. It must have very low performance overhead, or as low performance overhead as possible, and low developer cost. So developers generally don't want to rewrite their application to protect against or to enable a given mitigation. So let's now look through different kind of attack vectors and what kind of mitigations they spawned. And at the beginning of time, there was code injection. This was the most common and most frequently used way to attack software in the past. It's also the simplest way to achieve arbitrary code execution. You simply inject new code into the address space of a running process, redirect the control flow to this injected code, and bam, there you go. You've got full code execution and you can do anything you want. Right? So these are two easy and simple steps. You inject code into the process, into the address space, and then you redirect the control flow to the injected code. So one of the early defenses that were proposed was data execution prevention, or DEP. And here the underlying goal is to simply prohibit the attacker from injecting code. And the assumption was that if we prohibit the attacker from injecting code as data, then the attacker cannot achieve code execution. Done. And we no longer need to worry about any kind of attacks, right? Because an attacker may still be able to inject data, but this data that has been copied into the address space of the vulnerable process can no longer be executed by the CPU. And the CPU will have to distinguish between code and data. Now, one of the challenges was that earlier ISAs, all these instruction set architectures, for example, x86, the 32-bit or 16-bit version, and ARM, did not distinguish between code and data. So anything in an address space could be executed. Any data in the address space or any byte in the address space could be interpreted both as code and as data. And in code injection, an attacker redirects the control flow to a buffer that contains attacker-controlled data. And then this data, instead of being read in its original purpose, is actually executed by the CPU because the instruction pointer points to this data buffer and thereby happily executes it. So for data execution prevention, we change the address space and make sure that any byte in memory is either writable or executable. And this looks as follows, right? So without defenses, we have our address space that consists of text, all the code that is mapped to the process, data, and the stack, right? And the code, the text section, is readable and executable. The data section, which is the heap, and the stack are both readable, writable, and executable. And attackers could inject code in all these different areas. Now, if we enforce DEP, data execution prevention, we remove the executable bit from the heap and from the stack, thereby limiting on or prohibiting the attacker from injecting new code. The attacker may still inject data, but not code. Now, luckily, this was implemented as a page table extension where a non-executable bit is introduced. Now, there's the different companies. They all have large marketing departments that actually need to be paid. And Intel calls this per page bit execute disable. AMD calls it enhanced virus protection. And ARM calls it execute never. So there's an interesting mix between the marketing departments trying to outdo each other and the different companies trying to make sure that they have not copied from each other. Now, but what it does on the actual hardware is it introduces an additional bit for every mapped virtual page. If the bit is set, then data on that page cannot be interpreted as code, and the processor will trap if control flow ever reaches that page. Now, how is this implemented? And let's take a short detour on how the page table implementation is actually done. Now, in hardware, the page table looks as follows, and you will remember this from your architecture class on x86-32. This is a 32-bit address space with a two-layer page table, the page directory and the page table entry, and then the last 12 bits pointing to the actual page. This also means that in the page table itself, we have 12 bits to actually encode the different permissions and the different flags for the page table. The page table entry looks as follows. Well, the very first bit is the present bit, as in is this page mapped or not. Then we've got one bit for read and write. If the page is writable, we've got another bit for user and supervisor, and then different kind of flags and so on. Now, interestingly, we have no additional bits here to actually encode if a page is executable or not. The only thing we can encode is readable and writable. Every single page will be executable, right? If something is not, we've got one bit to toggle between read and write. And any page that is writable is also readable. So we've got three options: not readable, readable, and readable and writable that can be encoded here without any additional bits to encode executable or non-executable. Now, AMD and Intel introduced a physical address extension, or PAE, which actually makes this a 64-bit entry. So instead of 32-bit entries in the page directory and the page table, we now have 64-bit entries, which gives us some additional space to encode additional bits. Also, it allows us to have larger physical address spaces than 32-bit would allow. So this allows us, the physical address extension was introduced to have more physical memory than 4 gigabytes. So this allowed systems of the time to go beyond 4 gigabytes of physical memory, but each individual process, any single process, could only hold up to 4 gigabytes of memory. Now, if we look at this PAE, page table entry, we see that in the 64-bit entry, we have the same encoding of the first couple of bits, similar to the classic page table, but we've got this additional bit at the end of it, the 63rd bit. So the very last bit has execute disable, right? So if it is set, then this page cannot be executed, right? So this allows us to actually toggle the executable bit, and now extends the system to having the different states. For each page, it is either not present, it is readable and writable, it is readable and executable, or it is readable, writable, and executable. And this would allow us to implement the data execution prevention policy where any page is either writable or executable, by actually enforcing this in practice. Now, on a 64-bit system, we've got a slightly different layout of the page table in a 48-bit address space according to the Intel manual, as is being shown here. In a 48-bit address space, we go through the actual page table, page directory, and then the page directory pointer table through this three-layer lookup, right? And if we go through this and actually look at the page table entry on the 64-bit table, we have the same execute disable bit that allows us on a per page basis, on a per 4 kilobyte page basis, to toggle the bit if it is executable or not. Right, so this allows us to very cheaply, at like no additional overhead, implement data execution prevention where any page in memory is either executable or writable. Now, unfortunately, not all hardware supports these extensions, these address extensions, and there are interesting alternate implementations. For example, ExecShield used different kind of features on the x86 systems called segment restrictions to limit code executions on x86. OpenBSD's writable X or executable follows the same idea, and then PAX, which also exists for Linux, is a form of ExecShield on steroid, which is significant remapping of code regions across different libraries and processes to ensure that all the code is mapped in a similar area. Right, so there's, as you see, there's different ways to implement data execution prevention. Using hardware extensions is the cheapest way and the most commonly used way today. So let me summarize the data execution prevention policy. The policy is that data is never executable, only code is executable. The CPU most commonly checks if a page is executable on instruction fetch. On today's system, DEP is enabled by default whenever hardware support is available, such as for all x86 and ARM systems. And this stops all code injection. On a per binary basis, you can check if DEP is enabled or disabled for that binary as checksec. And when you're compiling, you can actually disable DEP with execstack, which allows you to still inject code. So for example, I think the most common use for this flag, for the execstack flag nowadays, is CTF challenges to allow simple code execution. Now, as we see here in the defense summary, if we enforce DEP, we get code integrity, and through code integrity, we can stop any form of code corruption. So far, so good. Now, unfortunately, DEP did not solve all attack vectors, but attacks got harder. Now the question how much harder they got is left to the interested reader, but there's other kind of ways to exploit the target, which we'll go into now. Code injection consists of two stages. First, redirect control flow to inject the code, and then data execution prevention stops the attack at the second stage, right? So the first stage is redirect control flow. The second stage, inject the code, or the other way around, inject code first and then redirect control flow. Now, what attackers can still do under DEP is to redirect control flow to existing code. And this gave rise to a new attack vector, namely code reuse. The attacker can still override a code pointer, such as a function pointer, a return pointer on the stack, the vtable pointer to an array of code pointers of a C++ object, or an exception frame for C++, right? Then prepare the right parameters on the stack, and for example, reuse a full function or parts of a function. So let's go through an example where we reuse a function with a single parameter. Okay, we've got this vulnerable function here where the data is being copied into a local function, and we simply compare the data that has been copied locally to a predefined string. So we execute this vulnerable function with the attacker controlled string. So we build up a stack frame that consists of the very first argument, the return address, maybe a safe base pointer, and then the additional like the array that is allocated locally. In the string copy, we first copy data into the buffer and overwrite all of the buffer. The attacker doesn't care. The attacker overwrites the base pointer, which is a memory safety violation because we are now starting to write past the end of the buffer. As a next step, if you just continue the writing to the buffer, we overwrite the return address. So instead of returning to the function that called this function, we are now encoding a pointer to the function, to the libc function system. So we have now violated code pointer integrity. As a next step, we also need to know where system in the address space is, thereby violating the randomization or knowledge of the confidentiality of code pointers, of the layout of the process address space. As a next step, we encode EBP after the call to the system function, and then we also store the very first argument to system, which likely is a string that will open a shell, right? So we have now encoded 3 slots on the stack, a code pointer to system, EBP after the system call, because this is expected by the target to be reasonable, right, when we're calling system, and the very first argument that we send to system. Now, as we continue execution, we return, and as we return, we violate flow integrity, as in the corrupted code pointer is being used, and we have executed a successful control flow hijack attack, and thereby the attacker gains control and finishes this attack. Okay. So far so good. So we've now shown a simple example where we reuse one function in the libc by encoding the target address on the stack and then encoding the additional parameters on the stack as well. Now we can generalize this from function reuse to full return-oriented programming. Instead of targeting a function, we can target a gadget. Instead of targeting one function, we can target multiple gadgets that are chained to each other. So a gadget is a sequence of instructions ending in an indirect control flow transfer, such as a return, an indirect call, an indirect jump, or whatnot. We prepare the data and the environment so that, for example, pop instructions load attacker-controlled data into registers. And an invocation frame looks exactly what we prepared before with the pointer to system, the EVP after the call, and the first argument to system. And then we just chain the sequence of invocation frames to each other. So the invocation frame for a gadget consists of a sequence of 0 to n data values and then a pointer to the next target. The gadget uses the data values and transfers control to the next target. Now, let's look at what kind of ROP gadgets actually exist in a target. And for those, we can simply use a tool such as ROP gadget or any kind of other tool that exists, which will then list all the interesting targets, which generally end in an indirect call. So the very first target would require us to encode the target of the next gadget in RSI. The second gadget requires us to store the next target in a given memory location, and so on, right? It could be on the stack for return instruction or whatnot. I invite you to play with this tool to figure out some of the details and how to connect the different bits and pieces a bit. And you'll gain more practice in the labs to figure out how to actually align these targets and play with ROP payloads. Now, if we have more complex shellcode that we want to execute, we can translate it into ROP sequences. So we've got the shellcode here: XOR EAX, EAX, XOR EBX, EBX, INC EAX, and then int OX80, which is a simple system call to terminate the current process. Now we need to find gadgets for each instruction. So the first gadget is XOR EAX, EAX, followed by a return, XOR EBX, EBX, followed by a return, INC EAX, followed by a return, and then the last instruction is just a location for int OX80, which will execute the system call. Now, none of those have any parameters, so we'll simply chain the different invocation frames next to each other. So, and write on the stack first the address of the first gadget, then the second gadget, third gadget, fourth gadget, and one after each other. By executing it, the control flow will execute XOR EX, EX, pop the next frame from the stack, XOR EBX, EBX, pop the next frame from the stack, INC EAX, pop the next frame from the stack, and then execute the system call, and we're all done with our exploit and have actually executed the full ROP chain. An interesting aspect for gadgets or return-oriented programming is that we often need to pivot the stack. Sometimes the buffer where we can store our invocation frames is not directly on the right next to the function where we have the buffer where we have the issue, right? Now we may need to adjust the stack pointer. Now, interestingly, there's gadgets that are called stack pivots that allow us to either increment, decrement the stack pointer, or just set the stack pointer directly to maybe to the heap, right? So we can make the stack pointer ESP or RSP point to any arbitrary location in the address space. We just need to find the right gadget to actually do that. So this is often used if we, in the very first buffer that we control, we only have a single gadget or whatnot, or space for a single override of the return instruction pointer. So we can jump to this first gadget that then adjusts the stack pointer, thereby allowing us to launch the full sequence of ROP gadgets that follow. Now, how do we fully mitigate code reuse? How do we fully mitigate this issue? Now, it's hard to do, right? It's hard to protect control flow against control flow hijacking, and we'll talk more about this in the next lecture, where we'll talk about control flow integrity and stack integrity as two main parameters. Now, a defense that we actually have in all the systems is address space randomization, because a successful control flow hijack attack depends on the attacker overriding a code pointer with a known alternate target. And address space randomization randomizes and changes the process memory layout whenever a process is executed. And the underlying assumption is that if the attacker doesn't know where a piece of code or data is, then it cannot be used in the attack, and the attacker is unable to abuse their privileges that way. So the attacker would first need to learn or recover the address layout before being able to execute the attack. Now, the security improvement of address-based randomization depends on the entropy that is available for each randomized location. So if the attacker can guess it, then that's not enough. The completeness of the randomization, if all the objects are randomized, and the absence of any information leaks. So if the attacker can simply leak the location of the different targets, then the attacker could bypass the actual defense. So what are good candidates for randomization in ASLR? There's a trade-off between overhead, complexity, and security benefits. So for example, you can randomize the start of the heap, the start of the stack, the start of code, randomize mmap allocated regions, different allocations. For each malloc call, you can randomize the code itself, gap between functions, order of functions, basic blocks, whatnot. Randomize member of structs on the data side, so it doesn't always have to be code. You can change the padding, you can change the order, everything you like. And there's a whole research area on fine-grained randomization, which focuses around the topic of software diversity, which you can look into if you're interested. Now let's concretize this a bit. After the proposal of address space randomization, it was refined into address space layout randomization. So ASLR is a practical form of address space randomization. Instead of focusing on individual basic blocks or functions or whatnot, ASLR focuses on blocks of memory, as it is much more coarse-grained. So it focuses on the heap, the stack, code areas, the executable itself, mmap regions, and whatnot. ASLR is inherently page-based, which limits the cost of shuffling, and it generally can be implemented through a cheap hack in the operating system with a little help from the loader and the compiler to make sure that the references are encoded in the right way. The entropy of each section in ASLR is key to security if all the sections are randomized. The attacker usually follows the path of least resistance, as in targets the object with the lowest entropy that is useful to them. Early ASLR implementations had low entropy on the stack and no entropy on x86 for the main executable. So the attacker would thereby, for example, if there's an infinite amount or large amount of threads, would simply aim at launching these threads or attacks against threads until they guess correctly. Similar, if the entropy is low enough, you can simply start the program many times to actually bypass the defense. So if you look at how ASLR changes the address space, the page table or the address space is now shuffled, right? The attacker will no longer know where in the address space individual pieces of data, text, or the stack actually are, thereby making it harder for the attacker to find where they need to attack, right? Or where the data that they want to use actually lies, or the buffer actually is, right? So they add uncertainty, making it harder for the attacker thereby. We can also combine ASLR and DEP so that both the permissions are being removed. So we remove the executable bit for stack and heap, and also randomize stack, heap, and text sections. So if we summarize ASLR, the ASLR leverages randomness to shuffle the address space, and to execute code, the attacker must know where the code actually is. So ASLR is a probabilistic defense that protects against code and database attacks. It's extremely lightweight when orchestrated by the OS, compiler, and loader, and can be implemented at almost negligible overhead. It's not a complete protection, so it is probabilistic, but it makes the underlying attacks much harder. Cool, so far so good. What's next? The next defense is stack Canaries. And this is a defense that actually survived to protect the stack. It solved an imminent problem because early attacks and then return-oriented programming uses buffer overflows on the stack to inject code or to inject invocation frames. Now, memory safety would mitigate this problem, but adding full safety checks is infeasible due to the massive kind of performance overhead that you would have to pay. Instead of checking each pointer dereference, the idea behind stack Canaries is to simply check the integrity of the system before important data is accessed. And this is the return instruction pointer for stack canaries. So the assumption here is we only prevent the control flow hijack attacks that target the return instruction pointer and only protect against continuous overflows from the stack. So no protection against direct overflows of the target. So let's look into how stack canaries are actually implemented. Well, the idea is fairly simple. We place a canary after a potentially vulnerable buffer. So if you have a stack, right? The stack contains both the return instruction pointers, code pointers, and actual data. Now the data, the buffer, the potentially vulnerable buffer, as decided by the compiler, is protected or is separated from the other data by placing a canary in between the buffer and the other data. Now before the buffer is being used, the canary is initialized with a known safe value, and afterwards this canary is checked if it is still valid. If the canary is no longer valid, as in the value has changed, we know that a buffer overflow has overwritten this value as some arbitrary data. So this only protects against continuous overwrites if and only if the attacker does not know the canary. An alternative would be to return an instruction pointer by storing it as a secret, but that's an implementation that didn't gain traction. But let's look at this in an example. So we've got this unsafe function here, where we have a buffer foo on the stack, and we string copy data into this buffer. And this results in the code on the right-hand side, where we push the base pointer, we adjust the stack pointer, we make space for our local buffer, we move things around, we adjust the parameters, we call string copy, and then we leave and return. Now, if you look at the stack canaries or stack protector as used on Linux, it adds two snippets of code. One snippet in the function prologue that is shown on the top, and one snippet in the function epilogue. In the function prologue, it loads the stack canary from this per thread page, which is per thread shared storage, and pushes it into the RAX register, moving it to the stack and then clearing the register after it is done. Now at the end of the function, it loads the value of the canary from the stack and compares it against the value stored in the thread. If they are equal, all is good, and we simply exit the function. If they are not equal, then we know that a buffer overflow has happened, and we call stack check fail. So far so good. So to summarize stack canaries, they protect against continuous buffer overflows by placing a canary between the buffer and other data. The canary is stored in a safe location, copied to the stack slot in a prologue, and checked in the epilogue before returning. And this protects against most stack-based hijack attacks. It is a simple defense, low overhead, enforced by the compiler, and simply adds a couple of instructions to functions that may contain a vulnerable buffer. Another data structure on the stack that is vulnerable to exploitation is exception handling metadata. Exceptions are a way of indirect control flow transfer in C++, and a safe alternative to set jump, long jump. Safe in a way from programming semantics to enforce structured control flow. So it makes control flow semantics explicit in the programming language and allows actual checking of exceptions in the programming language. Now the implementation can still enable exploitation if the attacker can control and modify this metadata of the exception handling information on the stack and adjust it to their need. Exceptions allow this handling of the special conditions and should recover from thrown conditions. So if you look at an example here, we've got a function that divides two doubles, and if the b is 0, it throws a division by 0 exception. This function is being called at the bottom, where we try and catch the exceptions it is thrown. Exception handling requires support from the code generator, the compiler, and the runtime system, which is libc or libc++, and is compiler specific. So LLVM, for example, uses libunwind. There are two implementations. You can either inline exception information in the stack frames itself, or generate the exception tables that are used when an exception is thrown. Now, inline exception handling stores this additional metadata on the stack. The compiler generates code that registers the exceptions whenever a function is entered, and individual exception frames are then linked across stack frames. So allowing the compiler to figure out where we are, what kind of information has to be unrolled from the stack, how the stack has to be adjusted, where the local variables are, and so on, to enable the runtime system to trace this chain of exception frames to the actual corresponding and correct handler that will actually handle this exception. It's very compact, but results in overhead for each function call, as the metadata needs to be collected and analyzed and pushed, right? So these are additional instructions that need to be executed. On the other hand, we have exception tables, where the compiler emits for each function and for each object a set of tables that link code addresses to program state with respect to exception handling. As in, there's a table that encodes at this location. These variables are in the registers. These variables need to be unwinded. This is where the different targets are and whatnot. Throwing exception then becomes a range query in the corresponding table and locating the correct handler. So this is additional code that is being executed when an exception is thrown. These tables are encoded very efficiently, so the decoding requires additional processing and an additional computation. So decoding an exception or catching an exception is extremely expensive, but in the case of no exceptions, this becomes performant. And this is exactly the trade-off, right? With the exception table, or with exception tables, we have to record and mark in the table what kind of exceptions could be thrown and whatnot. And when exceptions are being thrown, we use the return instruction pointers on the stack, walk backwards through all the stack frames and infer where we are, recover the information by walking the translation tables. So this requires some heavyweight computation for each exception that is being caught, but no overhead for exception if no exception is being thrown. Now, on the other hand, we've got inline exception handling, that whenever you call a function, the function prologue needs to execute this additional code to store all the metadata on the stack. This makes this much easier to process, but has the cost for each function call, even if no exception is being thrown. Right? So there's an interesting trade-off between the two implementation approaches. Now, if you look at Windows, Microsoft uses a combination of tables and inline exception handling. The stack frame records the unwinding information, set of destructors that need to run, and the exception handlers if a specific exception is thrown. When entering a function, the SEH record is generated, pointing to a table with address ranges for try-catch block and destructors. So this means that we only need to store one pointer for each function that contains exception handlers and try-catch blocks, which is a good compromise between the two. Now, oddly, in this situation, the attacker may overwrite the first SEH record on the stack and point the handler to the first gadget. Microsoft therefore developed two defenses, safe SEH and SEHop. Safe SEH forces the compiler to generate a list of allowed targets. If a record points to an unknown target, it is rejected. And SEHop initializes the chain of registration records with a sentinel. If the sentinel is not present, so the exception handler routine always walks to the end of the list. If the sentinel is not present, the handler is not executed. Now, an attacker can still reuse and arbitrarily combine any of the exception frames that are present, thereby using those to implement interesting functionality. at the end terminating it with an actual fake sentinel, right? So it doesn't detect any kind of replacement, but this requires heavyweight arbitrary write primitives for the attacker. If we look at GCC or LLVM and how they implement safe exception handling, GCC encodes all exception information in external tables, and they encode for each instruction pointer which destructors need to run and what handlers or registers. This results in no overhead in a non-exception case, but actually requires quite a bit of computation when exceptions are being thrown. And it even starts an interpreter to decode the highly compressed data to recover all of the necessary information. Now this can be abused for Turing-complete execution, and there's an excellent talk by James Oakley and Sergey Bradas exploiting the hardworking dwarf, because the information that stores all of this information is called dwarf, which is the correspondence to the ELF file format used on Linux systems. Now, let me summarize stack canaries and safe exception handling. They protect the code pointers on the stack and mitigate contraflow hijacking. Full integrity is not possible, so validation occurs when needed, as in before the pointer is being used, before the return instruction pointer is being used, for example. Stack canaries can be bypassed by either leaking the canary or through direct override, and this gives us some protection against contraflow hijack attacks and limits what the attacker can actually do. As the next defense, we're going to look at Fortify Source, which protects us against format string attacks. We've had format string attacks in the last lecture, and they allow an interesting approach towards arbitrary writes. Format string allows the attacker to write to arbitrary memory through the %n primitive, also adjusting the stack slots and whatnot. The only sane approach towards mitigating memory safety issues or arbitrary writes through format strings is to deprecate %n, which is exactly what Microsoft did. So this was a breaking change in their standard library that they enforced, but that worked actually fairly well. Now Linux introduced extra checks for the format strings. These checks may make sense even for Microsoft, but deprecating %n would make even more sense. They check for buffer overflows if possible, check if the first argument is in a read-only area, and check if all arguments used in a format string are actually marked in a format string are actually used. Linux checks the following functions: the memcopy family, the string copy family, the string cat family, and the printf family. The GCC and glibc patch distinguishes between 4 cases. Known correct: if something can be proven correct by the compiler, there's no need for a check. Not known if correct but checkable. The compiler adds an actual concrete check. Known incorrect: the compiler will emit a warning. And not known if correct and not checkable, there's going to be no check, and the overflows may remain undetected, which is somewhat weird because the compiler may not tell you that it does not know if it is correct and it cannot check it. Therefore, there may be silent errors that are simply missed. Now, for example, in this code here, we have a buffer overflow to a local buffer. Here the compiler knows that the buffer is of length 10, and we may have a length of a buffer that is not known, passed from an argument. So it is checkable and we don't know if it is correct. Therefore, the compiler will actually add a check. In this end here, we have 2 assignments, P and Q, and then we string copy from one buffer to another. Here, oddly, this is not checkable as the size of both buffers is unknown, and the compiler cannot enforce any kind of check in this end, right? Now, this is somewhat limited, but it actually caught a bunch of bugs, especially against local or stacked local buffers. Now, this concludes the defensive slide, But let's look at return-oriented programming, or what we can do after we go beyond return-oriented programming. And we looked into control flow bending, where instead of just using return-oriented programming, we bend the control flow along alternate paths in the program. Right? A data-only attack would overwrite the arguments to exit. A non-control data attack would overwrite the isAdmin flag, as we've seen before. Now, control flow bending, compared to these two other attack vectors, would modify a function pointer to a valid alternate target, as in attacker-controlled execution along a valid control flow graph, generalization of non-control data attacks, where each individual control flow transfer is valid, but the executed trace may not match the non-exploit case. So, for example, in an if-else statement, both the if and the else block could be executed. If you're interested in knowing more, I refer you to the control flow bending paper. If we want to go beyond control flow bending, there's also block-oriented programming, where we express a payload in a C dialect, abstract this into a set of constraints, and then based on this high-level analysis from the target program, we find basic blocks that serve as computational primitives. We synthesize a path through all the candidate blocks, and then encode the attack as a state change, which is injected through a bug. This follows the program fairly closely, but allows or bypasses all mitigations and enables full arbitrary code execution in a high-level language. It's very, very hard to pull off, though, because it requires quite a bit of constraints and very deep control. Now, as you see here, right, there's a lot of opportunities of finding computation in odd and weird places. These bugs enable attackers to break out of program semantics. The existing program can enable powerful abstractions if executed with different data. And as it turns out, even format strings are Turing complete by themselves, and you can play with the printf example if you want to figure out more details about printf-based exploitation. Now, one note here is that arbitrary code execution may not be arbitrary computation. Arbitrary computation would be implementing a Turing machine. And arbitrary code execution is being able to execute any instruction. With some of the later defenses, we are getting closer to arbitrary computation, moving a bit away from arbitrary code execution. Because, for example, in the printf, printbf example, we could be simulating a Turing machine as part of format string decoding. But arbitrary code execution is hard. Assume your exploit is restricted to use only existing code, and existing code does not use floating point registers. Therefore, you would never be able to execute code that accesses or modifies these registers on the machine itself. But you could simulate a Turing machine that implements floating point numbers and could actually do any arbitrary computation. Right? So there's a fine difference between the two that you need to be aware of. For exploits, you generally want arbitrary code execution and not arbitrary computation. Now, summarizing the deployed mitigations, we've got data execution prevention, which stops code injection, address space layout randomization, which makes code reuse harder, stack canaries, which stops stack-based buffer overflows, safe exception handling, which makes exception hijacking harder, and fortify source, which stops format string bugs and many string copy errors. So this completely mitigates code corruption and makes control flow hijacking and data-only attacks significantly harder. Let me summarize. There's only few defense mechanisms that have been adopted in practice and rolled out broadly across many systems. We now know their strengths and weaknesses. Data execution prevention stops code injection attacks, but cannot stop code reuse attacks. Address space layout randomization is probabilistic, shuffles memory and the address space, but is prone to information leak. Stack canaries are probabilistic and do not protect against direct overwrites and are also prone to information leaks. Safe exception handling limits exception handlers, and fortify source protects static buffers and format strings. Thank you for your attention, and I'll see you for the next lecture.